All right. Can everyone hear me okay? Yeah? Awesome. My name is Stephen Tobe. I'm a lead program manager on the parallel computing platform team at Microsoft. And this talk is all about the many-course shift and taking applications parallel. Now, I've gotten a few questions on this already off to the side, so just to set expectations, this is an overview talk. We're not going to do a deep dive into any of the new programming models or anything like that. I will touch on them, but not a deep dive. So if that's the kind of thing you're interested in, there are several other talks this week, and I'll refer folks to those later on. You can also check out the slides for this, and there's a resources slide at the end that lists the other sessions. But I really like getting good scores at these talks, and I find that the worst way to do that is to set the expectations wrong up front. So that's what we're doing. And if you guys want to leave now, that's cool. If you want to stay, fabulous. All right. So just a little bit about what we're going to talk about over the next hour and 15. Also, while I do have an agenda, I also really like to be interrupted. So if you have questions, feel free to shout them out, raise your hand, whatever it may be. Interrupt me as we go. That's awesome. OK, a little bit about what we're going to talk about. Why parallelism at all? Why are we even here? I guess that's the question for the ages. But why are we actually at this talk? So why parallelism, and why now? Why are we talking about it in 2009? When this sort of work has been happening and work to enable parallel applications has been happening for the last 30 or 40 years. Why is that actually starting to be an issue today? And then, now that it is an issue, what are we going to do about it? What can you do about it today? And what's going to be easier in the future? How are you going to better tackle it in the future? And then, to kind of round it out, along the way, I plan to show a whole bunch of demos. I will try and stay kind of the high level, but I have a tendency to dive into code. So if I do so too much, yell at me. If you like that I'm doing it, I guess still yell at me. Just tell me to keep going. Before I keep going, just a show of hands. How many folks here would classify themselves as developers? All right, the majority of folks. How about IT pros? Several folks. Awesome. So because this is tech ed and this is for both IT pros and developers, I have tried to make sure it's good for everyone. Although because there are more developers in the room by a significant margin of like 99% or something. I will probably err towards showing just a little bit more a code and maybe diving in a little bit more along the way. All right. So just to set the stage, how many people here have not heard of Moore's Law? I figured. All right. So Gordon Moore, founder of Intel, back in 1965, he wrote this paper where he talked about the economics of transistors and how transistors would be coming down in size and in price, and you'd be able to basically, for the same amount of money and in the same amount of space, fit twice as many transistors as you did 2 years ago. The time frames he actually outlined in his 1965 paper were a little iffy. It was somewhere in the 18 to 24 months, and he didn't actually put a solid time on it. But later on, he refined it, I think about a decade later in 1975, to what we know of today as the number of transistors incorporated in a chip will approximately double every 18 to 24 months. That's pretty awesome. And this is what's really fueled the software industry over the last 30, 40 years in many, many ways. This doesn't just apply to clock speeds of chips. This applies to memory. This applies to hard drives. Pretty much in any aspect you look, from the 60s through the 90s, you saw this doubling every 18 to 24 months of whatever hardware it was we were working with. And this enabled some amazing things. We'll talk about this a little bit more, but if someone asks, I've heard Moore's Law is dead. Everyone's talking about parallelism. Moore's Law is dead. Moore's Law is not dead. Moore's Law actually continues, and it's estimated to continue for several generations of processors and computers and the hardware industry in general. In fact, if you look at the past 30, 40 years, we're seeing basically this straight line. Now, we're purely talking about transistors at this point. We're not talking about what it means. We're just talking about number of transistors. And in fact, in 2006, with the Intel dual core something or other, we actually surpassed the 1 billion transistor mark. I mean, that's amazing that you can fit these many transistors. And this continues. So the question is, what does this actually do for us? Moore's Law is alive and well. Great. What's the problem? Well, you start looking at this from other angles, and things also start increasing at a similar rate. You start looking at the power consumption that's necessary to power this number of transistors, and this number of transistors packed into that small of a space. And the things that the hardware manufacturers are having to do with miniaturization and getting things down to 45 nanometers, which I believe is smaller than the wavelength of light. It's really, really, really tiny. Lots and lots of stuff packed into a very small space, leaking a lot of energy. The more and more of the stuff you pack together, the more and more power is required, not just to power the device, but to actually power what's being leaked out. And you get to points where, this is my beautiful quad-core laptop up here with a brick of a power adapter that's basically the same size as the laptop. It looks like the Xbox power adapter, and I'm carrying around with me. I think this thing is about 250 watts. It's just enormous. And so you start looking, not only am I getting faster and faster speeds, but I'm also getting more and more power consumption. Obviously, this can only scale so far, right? If in 2009 we're at 200 and something or more watts, and your gaming machines are at 500 watts, 2 years out, 1,000 watts, 2 years after that, 2,000 watts, right? Sooner or later, you're talking about the surface of the sun in terms of how much power is actually consumed. And in this case, this is actually frying an egg on top of this CPU, just outputting a huge amount of power. And it's not only a problem from having bricks this size, it's also a problem from the cooling systems that you need to keep these things cool. This laptop has a pretty powerful fan system built into it, and that's with the power supply separated out, just to cool the CPUs and so forth. And in these big gaming rigs, you see these monstrous fans, and people spend all their time trying to figure out how to make them less noisy while still getting these massive cooling systems. So obviously, this is a problem. Another problem is all of these sort of physical limitations that the hardware manufacturers have started running up against have decreased, in effect, have changed what people have viewed as Moore's law. So people talk about Moore's law in terms of transistors, but a lot of times people think about it in terms of clock speed, because for a long time they were largely synonymous. Right? Every 18 to 24 months you'd go out and buy a new computer, and it was twice as fast as the previous computer you bought. And this was for a lot of reasons. The hardware manufacturers were able to take that doubling of transistors, and in effect they were able to translate it into a doubling of clock speed and other things that made your computer run twice as fast. But recently this has started to slow down. And in fact, if you look at this curve, you can see what was this kind of gorgeous exponential straight line has started to taper off. And in fact, I'm curious, how many folks in this room actually have a 3.8 or higher gigahertz laptop or desktop machine? How many have a greater than 3 gigahertz? Maybe 25%. How many have between 2 and 2.5 gigahertz? Okay, the majority of people. Right, so this curve hasn't even just flattened off. It's also, in a sense, decreased. Now, that's not an exact fair comparison. There are other things to think about when you're talking about this stuff besides just clock speed. But it's a fair approximation when talking about it. There are lots of what are called walls that the hardware manufacturers have run up against. They've run up against these heat issues, packing more and more transistors into a finite amount of space. They've run up into instruction-level parallelism issues, where a lot of the benefits that you saw in performance actually came from the hardware manufacturers figuring out how to look at a sequence of instructions and overlap them to some degree, so that you could potentially, if I had three instructions in a row, the second and third of which weren't dependent on the first, well, you could run them side by side. Or if there was a branch in my code, I had an if statement or a while loop, the hardware could actually try and predict what was going to come next and run that at the same time. And if it failed, oh well, it throws away its results. It's called speculative execution. And with tricks like this, using all these extra transistors to get that extra kind of hardware-based performance, they've been able to continue kind of clocking up the performance that you got out of the hardware. But in effect, they've reached the end of being able to do that. They sort of optimized it as much as they can. And while there's still a little bit left, it's not nearly the 50% per year that we had been seeing. And in fact, if you look at where things are going, you might get another 5 to 10% each year out of your clock speed, out of your processors at the rate things are going, and maybe a few more times. So maybe in the next year we'll see another 5%, and the year after that another 5%. But eventually it's just going to stop. Moreover, that 5% is going to cost you twice as much power, or 3 times as much power, or whatever it may be. These modest increases come at a huge cost in terms of heat dissipation and power consumption, giant bricks that are going to start sending me to the hospital. This is just not the way to go. So while Moore's law is still alive, it's alive in a very different manner. This, by the way, is a chart of power density, and you can see we actually are on a path to hit the sun's surface. Currently, we're somewhere around a nuclear reactor. But if you talk to Intel or AMD or any of the other hardware manufacturers, for the last several years, they've basically been saying, there's a new paradigm here. We're going to have to change directions. Moore's law continues. We still have these transistors. We still have them at this exponential rate. But we're going to start doing it in a parallel fashion. Rather than putting them all into a single chip and trying to make those, that chip faster and faster, we're going to start adding more cores. So this is from Pat Gelsinger in 2004, basically describing what he thinks architectures will look like in the future. You'll have multiple cores per die. You'll have multiple dies per machine. And in fact, you can see this in reality. If, wrong machine. If I switch over to, this is my quad-core laptop, but I'm actually terminal serviced into a machine back in my office. This is 24 cores, which is, let me just make this a little bigger. Quite a nice toy to have.
Is there a raffle for that?
If there is, I'm automatically going to win. Because I have to share this with other people, and, I never went to kindergarten, I guess. I don't like sharing. But you start to see where things are headed, and in fact, we really are headed towards machines where, in mainstream architectures, you're going to see 24 cores, 80 cores, 128 cores, whatever it may be. Some of those will end up being kind of the CPUs you're used to today. Some of them will end up being targeted at specific operations like graphics processors and so forth. But in order to take advantage of those, or rather, if we don't take advantage of those, we're going to be at a real disadvantage. So as a software developer, someone trying to get better bang for your buck out of software, make your company money, whatever it may be, if you look at if we were to imagine that, let's say we did get the 10% per year, that was like the best we could possibly hope for, and we were getting 10% per year, that's that purple line. And then we were able to continue ramping up our operations per second with parallelism, that's that green line. You get out to the year 2015, and we're at about an 80x gap between what you could accomplish sequentially and what you could accomplish in parallel. That's a huge margin, such that if you're not writing parallel applications, and you're not taking advantage of parallelism for all your computation, you're going to be losing out on a lot of kind of speed, and speed is money. So a couple quotes to kind of drive this home. Justin Ratner is now the CTO of Intel. This was a comment he made more recently in February of 2007, basically talking about Intel's architecture, saying they're going to hit the 80-core mark in mainstream processors. Can you imagine having 80 processors in a laptop or in your phone? That's pretty amazing. And that's in the next 10 years. Then you look at someone like Herb Sutter, who's an architect on the C++ team. He was also really big in the C++ committee, the standards committee. I think he was the secretary for many years. Basically, he wrote a paper back in 2005 called "The Free Lunch is Over." This was for Dr. Dobbs. And it's a very applicable term. He's basically saying that software developers for the last 30 years, 40 years, have relied on the free lunch. That being, they can write their software, and if it's not fast enough today, no problem. It'll be fast enough in 2 years when everyone goes out and buys a refresh of hardware at the company or whatever it may be. But that free lunch is over. Now you write your software and you expect things to get twice as fast. But if you write it in a sequential fashion, 2 years later, it's going to run at the exact same speed. And in fact, at the rate things are going, it's probably going to actually run a little bit slower because the hardware manufacturers can consume less power by not packing the transistors so tightly, scaling out to multiple cores, and so forth. So Herb's basically saying, now is the time to take a hard look at the design of your application and figure out how you can re-architect it for parallelism. And that's really where the industry is headed, whether we like it or not. That's where everyone is headed, not just Microsoft. You look at Sun, you look at Apple, you look at Oracle, you look at anyone out there. And this is where things are headed. So we really all do have to take a hard look at it and decide whether it's right for our applications or if it's not. And if it's not, we need to understand why, because it may be right for one of our competitors. Before I move on, any questions thus far? Pretty basic? Okay. All right. I'm convinced, now what? Right? That's a pretty compelling beginning. I should write parallel applications. Great. How do I do that, and why am I not doing that? Well, it's just plain hard. Even the experts consider it hard. You can write little components that maybe do a little bit of parallelism or do something in a very structured manner, and maybe you can do that right. But you start writing big applications that have a lot of things going on at the same time, that are targeting lots of shared memory, it's just plain hard. And I don't know if it's the case for all of you, but when I talk to a lot of customers, they pretty much verbatim, they always tell me that most people at the company they work at or in their software group doesn't know how to write parallel applications, doesn't have the background for it or the skill set for it. Rather, the company has some sort of strike team, SWAT force, developers, kind of the top 1% of developers that can do this stuff, that roam around the company and help to kind of get perf up to par, help to parallelize. They come in for several weeks or months, they help parallelize the portions of the code, and then they leave, going on to their next big assignment, leaving behind this mess of code that's now instant legacy because it can't be maintained by the rest of the software teams. Just by a show of hands, how many folks find that to be a similar experience, or how many, similar experience? All right, a handful of folks. Just by show of hands, how many folks have actually been doing parallelism in their applications? Wow, okay, so the rest of you that didn't raise your hands the first time, that just raised your hands, how many of you do find it easy to write parallel applications? 2 of you. 3 of you. All right, come see me afterwards. We have some open jobs. This is, I find this stuff very hard to do. All right, so even though you have these groups of folks that roam around companies and they're sort of the experts at it, apparently the 3 folks here, even for these folks, a lot of times it's redoing something from scratch. You look at the work that was done in kind of pioneering patterns and descriptions for common ways we go about implementing software with the Gang of 4 several decades ago, with common things like factory patterns and flyweight patterns and whatever they may be. You look at this for parallelism, and nothing really equivalent exists. We're starting to see some patterns. There was a recent book that came out from a guy at Intel, Tim Mattson, which starts to talk about kind of patterns. There's been some things here with the high-performance computing over the last 30 years, and some patterns have emerged. But they're really nowhere near as ubiquitous as they would need to be to really allow mainstream developers to take advantage of parallelism. On top of all this, there are just a huge number of problems, right? We run into bugs when we write normal sequential code, but when you write parallel applications, you really open a giant can of worms. This is a picture from, I think, New York City, kind of your typical deadlock. But we laugh, and I found this really amusing, so I had to put it in. But this is what we run into all the time with parallel applications, and this is just one class of problems. You have your deadlocks, you have your live locks, you've got your race conditions, you have your lock convoys, you have your priority inversions. Whatever they may be, there's just a huge can of things you don't really think about when you're writing sequential applications, and yet they have to become forefront in your mind when you're writing parallel applications due to the tools that we have today and the program models that we have today. And so one of the things we really have to do going forward is make it significantly easier for developers to write parallel applications. This includes better programming models. This includes better tooling support. Because at the end of the day, even if you're an expert in concurrency, I can almost guarantee you, for the most part, your businesses or the companies you work for don't want you spending all of your time focused on concurrency. They want you spending all your time focused on what it is that makes the company money. Now, obviously, having better performance than the next guy, to some degree, makes them money. But if you imagine that performance is just ubiquitous and everyone's going to benefit from kind of increased core count, what really makes the business money is their core value. If you're a component vendor, it's implementing great components. If you're an ASP.NET website developer, it's in implementing kick-ass websites. It's not making it run a little bit faster with parallelism. So at the end of the day, we really do want to make it possible for all developers to get back the free lunch, to be able to say, I'm going to have that performance as if my hardware was increasing at the same rate as it was and in the same manner that it was. All right. So I'm basically done with overview material, and we're going to start getting into a little bit more nitty-gritty and some code. I think this is also the last code I actually have in slides. We'll do the rest in Visual Studio. But just as a simple example, I was actually talking with a customer that was in the race car market, and so I threw together this example, and I figured I'd carry it over. Imagine you have a whole bunch of race car drivers, and let's say hundreds and hundreds of megabytes worth of data that you want to process through. And I want to search this data for, or in effect, aggregate it in a particular way. I'm looking for drivers that match a particular name that I might have typed into the UI that may have had a certain number of wins in some time frame, whatever it may be. As I find those drivers, I'm going to explicitly add them into my results set. And then when I'm done searching through all of my drivers, I'm going to sort them, in this case by age, and I'll display a histogram or something. So it's great. Sequential implementation looks fairly easy. The type of code we might write, right? This looks pretty standard. Now if I want to parallelize it, I start getting into code that looks a little bit like this. And before people start reading through this in depth, let me preface this by saying that this actually isn't all that great in implementation, and I'll walk through why. In fact, I haven't actually tried it, but I think this would actually run slower than the sequential implementation, even though it's parallelized. That's not to be self-deprecating. That's just to say that this stuff is hard to do. All right, so here's my manual parallel solution. Again, I have my drivers at the front and my result set. So far, we're looking identical. But now I have to start being concerned about things like the number of processors in the machine. Right? So I'm going to go parallel. I need to know how much parallelism I actually have at my disposal. If I'm going to take advantage of multiple processors or multiple cores, I do need to be concerned about when all the work is done on all those cores. So I want to be able to keep track of a remaining number of work items that are still left to be processed on all those cores. Because I'm no longer doing this sequentially and I need to have multiple threads sharing the same data source, rather than using a for each, I'm explicitly grabbing the enumerator from my driver's enumerable. And now, in order to basically block waiting for, let me just use the mouse to highlight where I am. We're right here in this manual reset event. Rather than using, in order to basically block until all of the operations have completed on all of my processors, I need to create a manual reset event here so that my main thread can wait on that and the background threads can signal it when they're completed. And then based on the number of partitions I want to use, I spin up the number of work items to go off and do their thing. Ignore this code here for a moment. Once I've spun those things off, I immediately wait on that event. And only when that event has completed do I then do my sort. So I've got a whole lot of background processing happening. And then once it's done, I'll do my sort afterwards. Now that background processing, let's say I'm on a quad-core machine. I've got 4 threads then that are going to be executing this code, which I've spun up on the .NET thread pool. Because I'm sharing this enumerator, I'm going to lock on the enumerator. So I have to do some synchronization here. And I have to explicitly call move next and then get the current in order to get the next driver to be processed. And only then, once I've done all of that work, do I actually get to the guts here of my previous operation. And even then, I'm actually doing some locking here. So if we actually look at the code that was maintained from the previous sequential solution, you can see it's hidden in maybe 4 or 5x times the amount of boilerplate that it actually took to get to this. And as I said, this actually isn't all that good in implementation. So why isn't it a good implementation? Well, I'm having to do manual partitioning. That's not very cool. I'm having to deal with threads explicitly or the thread pool explicitly. I have to know about synchronization primitives. Why did I use a manual reset event versus an auto reset event versus a critical section versus a semaphore versus whatever it may be? Why manual reset event and why did I pass in false? I have to do explicit locking. And not only that, I'm doing very, very, very fine-grained locking, but in a bad way. If you look at the amount of code that's contained in this lock and the amount of code that's contained outside of the lock, the reason this is going to run slower is there's probably actually more work inside here than there is outside of here. So I'm going to actually spend most of my time serialized inside this lock. So even though I think I'm running sequentially, or in parallel, I'm probably actually running serially, where a thread blocks waiting for every other thread to grab a piece, and then this thread grabs a piece and blocks all the other threads to do it. And you basically get this kind of, if you look at this on a big chart, you kind of get this step fashion where each thread, only one thread is running at a time doing this processing, and thus all the overhead actually makes it run even slower. I have to do weird tricks with interlock decrement here in order to be able to signal to the main thread that I'm actually done. Other very subtle things, like at the end here, I'm running on a quad core. I've spun up 4 background operations, and then I immediately, where's my cursor? Then I immediately block this main thread. So if you think about it, I actually have 5 threads here. I have the one that's being blocked, and then I have these 4 background ones. And that one that's being blocked consumes memory, right? By default, there's a megabyte of stack space that in .NET is committed right up front. This is a thread is known to the kernel, so the kernel has to do some processing associated with having this thread. And even the wait one call itself, that's a kernel call, right? Not only is this a p invoke to get out of manage, but then I have to dive down into the kernel to wait on this synchronization primitive. It also incurs a context switch, all this kind of stuff. And then finally, my favorite one is this sort. I've done all this work to try and go parallel. All this work is order n. You kind of look at this from an algorithmic complexity standpoint, except for the sort, which is order n log n. So that's the biggest operation, and yet I'm doing it sequentially, because .NET today doesn't have a parallel sort. So I tried to parallelize the portion of my app that wasn't even the slowest, and then the part that isn't the slowest, that's the fast, that requires the most processing, I was doing sequentially. So obviously, we don't want you to have to do that. So what's the answer? Well, this is today's world. We don't like today's world very much. We'd like to move forward. So let's go back to the sequential implementation for a moment. If you think about what I was doing, I was really taking a high-level concept of basically searching through some data, filtering it based on a certain criteria, sorting it, and projecting the results. And if you think about it like that, having to write it using a for loop and explicitly adding into a collection, that was me explicitly telling the computer at a very high level what I want, or how I wanted it to do something. Not only was I saying what I wanted done, I was telling it how I wanted it done. But by telling it how I wanted it done, I didn't give it any flexibility. Right? I didn't allow it to say, well, I know you told me you wanted it done this way, but I really think you wanted it done this way, so I'm going to do that instead. Because maybe that would work 9 times out of 10, but 1 time out of 10, it's going to seriously cause problems. So can't do that. Instead, you look at something like LINQ, Language Integrated Query. Just show of hands, how many folks are familiar with LINQ? Pretty much everyone. Awesome. You take something like LINQ, where it's really a higher level model. So this is C#, and it's basically allowing me to say exactly what I just described. For every driver, run some filter, sort it, and project the results. In this case, the projection is just the original value, but I could have selected driver.age. This is doing the exact same operation, but now I'm telling the system what I want done rather than how I want it done. And in doing that, you can imagine providing something like as parallel, which is just a directive to the system that says, hey, I want you to do this a different way. Even though I'm telling you what I want done, now take this directive to say, and oh, by the way, it's cool if you use parallelism. I'd like you to do that. And then the system under the covers could go ahead and do that. And while this looks like this cool, fanciful thing, this is actually something that's being delivered in .NET 4.0. So this is something that's called plink, or parallel link. So I've heard some people pronounce it plink. That sounds nice. Not how I pronounce it, but that's cool. Question?
So the driver's object is an IEnumerable. Is that to say that in 4.0, as parallel is going to be an interface on the IEnumerable? Is that what you're saying?
So if I could rephrase the question, I think the question was, more grandly, what does as parallel apply to? How is that actually structured in code, and what does it work with?
Is it provided through IEnumerable in 4.0?
I see. Gotcha. So the question is as parallel on the IEnumerable interface?
Yes.
So the answer is no. The reason as parallel isn't on the IEnumerable interface itself is because that would be a breaking change. So if you're already implementing an interface and then I go ahead and add a new method to the interface, I've now broken you because you're not implementing that interface method, and now you won't compile. What this is done is just like the rest of LINQ, this is an extension method on IEnumerable, which I think was the first part of your question that you alluded to. So just like the rest of the LINQ object model, which provides select, where, order by, join, group by, all that kind of stuff as extension methods on the enumerable class for IEnumerable. Oh, actually, I may have misheard your question. Were you asking if it was on enumerable, not IEnumerable?
You're going in the right direction. Keep going.
Okay, great. All of LINQ is basically on the enumerable class in system.link.enumerable as static extension methods for IEnumerable. As parallel is an extension method on the parallel enumerable class in the same namespace in system.link. And it's in the same DLL, in fact. It's in system.core. So I can show you this, but if you're using, you create a new project and you're referencing system.core, which you have to be to use LINQ, as soon as you start typing your enumerable, your drivers in this case, and I hit dot, as parallel will show up in the list, because the compiler will find not only the enumerable class with extension methods, but also the parallel enumerable class with extension methods. And it will see that as parallel is an extension method for IEnumerable. The actual concrete type that it's on, whether enumerable or parallel enumerable, for all intents and purposes doesn't really matter. The only time it matters is if you're using a language not like C# and not like VB that doesn't support extension methods. And thus you'd need to call it as a regular old .NET static method. Does that answer the question?
Yes, thank you.
Awesome. Cool. So why don't I actually, I'll show an example of this. Oh, yes, sir.
Why implement it as an extension method? Why not be just another type of build? The compiler
Why couldn't the
choose parallel?
I see. Got it. So the question is, if I can try and go more broadly, why do I even need to specify as parallel at all? Why couldn't it be more like this, and it could just run in parallel. Is that a fair approximation?
Yeah, when you build the code, it automatically, instead of just 64 32-bit builds, you have a 64 multiprocessor build.
That's a great question. So why couldn't this just be a parallel build, and everything that was linked inside the application kind of automatically became parallel?
Yeah.
Okay. Great. So I'll answer this in a couple parts. The first part is there's been a lot of work over the years in being able to automatically parallelize code, or more specifically, figure out where code is parallelizable. So if I told the compiler to parallelize this, and I could add that flag, and I could tell it any link to objects query you see, treat it as if as parallel was on there. We could do that. We would run into a lot of problems, though. And these problems come from the fact that it's very difficult for a compiler to prove whether that's actually safe or not. And this gets into one of the, at least my primary fears, what keeps me up at night around a lot of the things we're doing in .NET 4.0, is that we're eliminating a huge amount of boilerplate that and sorry, I should mention as well, as I'll talk a little bit more, this doesn't just go for .NET 4.0, this is also for Visual C++ 10. A lot of the things I'm talking about are for both managed and native. But back to this example explicitly, one of the things that really keeps me up at night is we're giving folks a lot of sharp knives. So as parallel is really, really cool. And for most cases, with link, it's perfectly safe until it's not. So as an example of where it's not perfectly safe, imagine that driver.age. Rather than select driver, imagine I did select driver.age. That's still safe, right? I'm just reading data. But then imagine I said select driver.age++. So now my link query is actually mutating the age of the driver in this collection. Well, so far, if drivers is a set, well, that'd be a pretty odd query to write. You could do it. It wouldn't be a problem. But now imagine that drivers wasn't a set. Imagine that Mario Andretti appeared multiple times in this collection. Now, again, the value of incrementing Mario Andretti's age twice in the same query would be a little suspect. But now I'm doing it from multiple threads. Because under the covers, parallel link is doing the same sort of it's handling all that boilerplate code for you. So now for multiple threads, I'm trying to increment Mario Andretti's age. And where I expected his age to go up by 2, it may have only gone up by 1 due to race conditions and whatnot with multiple threads under the covers. And it becomes very difficult for a compiler to figure out where those sorts of problems would arise. Imagine that age was a virtual property. At runtime, at compile time, the compiler doesn't know what age is actually going to resolve to. So it doesn't know if it's, if I'm accessing the same data or not. Those sorts of things become kind of a real thorn in the side of parallelism, and a lot of those sorts of issues are why it's not on by default. There are other things that are similar. For example, I may have written an application or be writing an application that expects the drivers to come out in order, right? Maybe they're already sorted. I do a drivers.sort, and then I process the drivers and expect them to come out, expect them to come out in the same order that I put them in. Maybe just filtered slightly. Forget the order by there, because obviously that would screw things up. But with parallelism, now I've got multiple threads processing through this driver collection. Some may be going faster than others. Some threads may be getting context switched out by the system. The net result is, in effect, the output is going to be random in terms of the ordering of the output. And if I was expecting the ordering to be the same as what I sent it in as, well, now I have a bug in my application that resulted from using parallelism. Could we fix that? Sure. Well, in fact, plink even provides, you can say .asParallel, .asordered. And it'll fix that ordering issue for you, but at an expense. And that expense may actually outweigh the benefits of parallelism depending on what you're doing. Because in the best case, we can actually sort of ensure that that ordering is correct as we go, and there's no extra work, well, very little extra work. In the worst case, we actually have to do a full sort at the end. And as I previously mentioned, sorts are expensive. There are other things you run into. Exceptions. Exceptions are kind of the prescribed way of doing error handling in .NET. Exceptions in .NET are based on Windows structured exception handling. You have one thread. You've got one exception in flight at any one point in time. And that's great for sequential code. I'm writing some code. It throws an exception. I process that exception, and I keep moving on. But in a case like this, when I'm executing this query, I have multiple threads doing work on behalf of, in effect, one thread. And now each of those multiple threads could throw an exception. And now I'm running into a situation where, in effect, one thread of execution has multiple threads that may be generating exceptions. And now I'm completely out of my world where I have one thread, one exception. And so we need a special way of dealing with that. In the case of plink, we actually aggregate those exceptions together and rethrow that aggregate. But if you had code that was expecting a specific exception to emerge and that there would be no side effects from other operations that may have happened concurrently, now not only could other operations happen concurrently while an exception was being thrown, you could have multiple exceptions being thrown, and now you're getting an aggregate instead of the actual exception type you were expecting. So there are lots of these sorts of issues where we basically made the decision, we have to make this opt-in. We even experimented in our initial CTP of plink with a namespace where you could basically say using system.link.parallel, and due to compiler binding rules, that would automatically change all link queries in that file to be parallelized. And even that we decided to get rid of because we really needed to be strategically from query to query, we need you to make the decision about whether to opt in or not. Long term, is that going to be the right solution? Well, probably not. I mean, if in the long term we can figure out whether something is actually safe, then absolutely. We'll want to go ahead and apply as parallel to it if we can make sure that it will behave identically to the sequential solution. But the chances of that happening in the near term are very small, and thus the opt-in method is the one we're going with. It was a very roundabout way to answer your question, I think, but did that get the gist of it?
Yeah, that's the gist of it. I mean, to me, you can set up the compiler to warn on potentially unsafe areas, and then the programmer could check each one.
So the comment was that we could set up the compiler to potentially flag unsafe areas and then kind of alert or basically inform the developer, hey, you might want to go investigate these things. That would certainly be a valid, one approach that could be taken. I would argue that you probably wouldn't want that to be done in a compiler. It'd be more sort of an analysis tool that you would run. And you'd really want your compiler to only target the ones that it was 100% sure could and should be parallelized. But it's a great point. Any other questions on that? Yes, sir. Was the question, will it run across machines?
Will it run on a single processor machine?
Oh, the question is, will it run on a single processor machine? Absolutely. In fact, let me just do a demo of this to kind of highlight that. So here we're back with our 16-core. Actually, let me switch back to my laptop for a second to show you the code. This is a very similar application. It almost follows the exact same structure. Rather than dealing with drivers, where I didn't have a lot of data, we went up to the Social Security database in the United States. They've got this cool online site where you can look at baby information, the most popular baby names in which state, in which year, and so forth. So we grabbed a whole lot of that data. In this case, we've got a few hundred megabytes worth. And I've got two queries here to basically process from a very simple UI where you input name and state and years, the most popular baby names, and to show a histogram. And you'll notice that this mirrors almost exactly the previous query. Basically, for each baby where the baby's name and state match particular criteria, we're going to order by the year the baby was born and select the results. And you can see the parallelized version of this, which is just using as parallel here, is doing the exact same thing except this extra bit of code. To get to the gentleman's question, this last thing here isn't actually necessary, but I have a track bar in the UI that allows me to configure the number of cores that are actually going to be used. And thus, I have this bit of code in here as well to allow me to kind of enable that track bar. So I'm going to switch back to my nice 24-core box and run that same application. I apologize. This is I'm a pretty good low-level developer, but this is about the extent of my my UI capabilities. I should really need someone who knows WPF better. But anyhow, I'm going to run the link version of this. And you can see here on this gorgeous 24-core machine, which my team spent a lot of money on because they're not exactly mainstream yet. We're only using about 5% of the available CPU. And if I make this bigger, let's see. One of these guys, there we go. This guy was basically pegged, and everyone else was sitting idle. In contrast, oh, wrong one. So that took about 21 seconds to run on 250 megabytes of data, searching for Stevens, born in New Hampshire. Now I want to run the parallel version. You can see it spikes up to 100%, and on this 24-core machine, it completed in just over 1 second for a 20.45x speed up. Which I think is pretty awesome. I like the joke that, I could come in the morning, have this application, tell my boss I was going to do some performance work, add as parallel at 9:05, go home at 9:10, and have a good day's work. So pretty cool stuff. Oh, actually, let me load that back up again. I didn't actually answer your question. So the question was, could this work on a single core machine? So yes, I'm running this again sequentially right now just to show you what this would look like. There will still be some overhead. So if we notice that we're on a single core machine, we do our best to maintain the parallel semantics that you would get, but kind of minimize the possible overhead. So we'll in effect run on one core, but there will still be some amount of overhead. So I'm going to put this down to just one processor to use, which is basically simulating what would happen on one core. And if I run the parallel link version, you can see I'm still, as with the sequential version, running on basically a single CPU with one thread. And it will probably be around 22 seconds or something, just a little bit slower than the sequential. But we can actually see. By the way, these are based on the almost beta bits of .NET 4.0 and Visual Studio 2010. So let's see. This took, well, actually, it was faster. That's interesting. So there's probably two things happening here. One is I wasn't being exactly fair to the sequential version because it got to run first, which meant that it was kind of warming up the caches and things like that first. That probably contributed a little bit. Second is because we are using parallelism, we had to implement our own algorithms, and some of the algorithms in some cases are actually faster than the sequential algorithms being used. Because we take that initial hit up front to do some query analysis to figure out what the query looks like and the best way to process it, which Link doesn't do. Because we've already taken that hit, we may actually run faster for certain cases. Sure. Good point. So we'll see which of those it actually is. That's a great question. The question was, is this linked to SQL or is this linked to regular collections? This is linked to objects, so this is over data in memory. Plink doesn't have a way of really working, kind of getting into a link to SQL or linked entities type query. No, it's still faster, so I guess it's the optimizations. It doesn't really have a way of getting into the link to SQL query. But if you look at what link to SQL does, it basically takes the description of your query, translates it into a SQL statement, and then remotes it off to the SQL box. SQL itself can do some parallelization of that query, and so plink really doesn't have a place fitting in there. Now, you can use plink on the results of a link to SQL query. So you could run a link to SQL query, get back your results, and then do processing of it, additional processing that you may not have done in the server. And you can do that processing in parallel. This leads to some pretty interesting things, right? If there's some work I want to offload from my overloaded SQL box and bring it back onto the client and distribute the work amongst my client, this can come in handy there. If you're using something like, Windows Azure, where the default storage model with tables with Azure doesn't provide things like aggregations and whatnot, well, you could take down the data and then do the aggregations locally in parallel. If you're doing aggregations across several discrete data sets, for example, I'm loading some data from 2 different SQL servers and then from a link to Amazon query and an XML query, whatever it may be, I can then aggregate and work on all that data in parallel once it's come into memory. But plink really is focused on in-memory parallelism. Yes, sir?
I just want to add, I think that this impressive example would probably fuel the fire to a lot of database admins who think that the only way to work with tables is in the database, which, I don't always agree with.
Cool. So for those folks that didn't hear, the comment was this would probably help negate, in effect, some database admins who believe that the only place to do processing is in the database. Did I approximate that right?
Yeah.
Cool. Thank you.
Power to the developers.
Woo!
Yeah.
Absolutely. And in fairness to those guys, there's certainly some logic to their argument. Yeah. All right. Cool. So let me switch back over. We'll come back and do some more demos, but I think we've beaten this one to death. All right. So Visual Studio 2010, .NET 4.0, Visual C++ 10, and so forth. All of this stuff is due out in beta form imminently. I don't have the actual dates. I don't know what I'm actually allowed to say, but I was really hoping it was going to be here this week, and it's not. But hopefully in the very near future, you'll be able to play with all the bits that I just showed. So Visual Studio 2010. Obviously, we already just talked about parallel link. Where is this guy? I can talk a little bit more about it. But this is just one piece of what we're doing, and I want to spend the remaining 30 minutes or so talking about some of the other stuff we're doing. The things that I have in yellow are the kind of our managed stack. The things that I have in blue are our native stack. And where possible, we've actually been doing a lot of the same work for both native and for managed. Now, in some cases, like with Link, there is no native equivalent to Link. C++, at least native C++, doesn't have Link. You could access it from C++ CLI, although I don't know of anyone that's really done that in a production system. So with something like parallel link, there's no real equivalent on the native side. However, with something like the task parallel library, which is on the managed side, we have the parallel pattern library on the native side, and these are really meant to be identical things. Moreover, on the native side, where we don't have plink, we have support for what's called asynchronous agents. And I'll talk a little bit more about asynchronous agents in a moment. Both the native and managed models have a collection of data structures for doing coordination, synchronization, kind of the bread and butter type stuff that you have to do in parallel applications today, synchronizing across a lot of threads with particular patterns, doing producer-consumer patterns, all that kind of stuff. We have solutions for in both the data structures and then on the native side in the agents library. And then all of this work sits on top of the runtimes. Now, on the native side, we've invested a heck of a lot of energy in building up what we call the concurrency runtime or concert. We have a lot of music acronyms that we like to use. Concert is really made up of two pieces. It's made up of a very efficient, fine-grained work scheduler. You can think of this as a thread pool, but kind of very robust thread pool. And that thread pool, or that task scheduler, executes all the work from the parallel pattern library, from the agents library, and so forth that sits above it. That task scheduler itself then sits on top of a resource manager where you can have multiple task schedulers in the same process, and the resource manager helps to ensure that they're not oversubscribing the box. You can imagine if in my baby example here, I had multiple queries that were executing at the same time, you don't want each of those queries to think that it owns all 24 processors, because that would cause a lot of extra work for the operating system. So then I have to say, all right, I have 24 times 3, and I have to figure out how to time slice between them and do extra context switches and all that kind of stuff. That costs. So we leave that up to the user mode resource manager to say, all right, if there's 3 of you, I'm going to give each of you 8 processors. And if one of you finishes first, well, then I'm going to allow this guy to take some of them, and then I'm going to reroute them over here when that guy's done, and so forth. And it handles all that kind of sharing, minimizing the actual overheads that are resulting from scheduling. On the native side as well, the concurrency runtime actually takes advantage of a new Windows 7 feature called User Mode Schedulable Threads, or UMS. I'm going to just briefly talk about this. There's 2 talks later this week that will dive into both UMS and the entire native stack, which I highly recommend folks attend if you're interested. But one of the things that Windows 7 provides is the ability for, rather than the kernel handling all context switching support, it actually elevates some of that up to user mode and allows a user mode application to actually make decisions around what runs next. For example, if I have a thread and that thread blocks, in today's world, the kernel says, OK, you're blocked. I'm going to go schedule somebody else. With UMS, the kernel calls back up and says, hey, one of your guys blocked. What would you like to do with the rest of your quantum? So if you were executing for 10 millisecond quantum and you ran for a millisecond of it and blocked, rather than kind of foregoing the rest of your 9 millisecond time slice, the kernel calls back to you and says, you got 9 milliseconds. What do you want to do with it? UMS also allows the application to say, I know I'm about to block. Rather than actually blocking in the kernel, I'm just going to do that little switch myself, and the kernel I don't need to tell the kernel that I was doing this, which saves the round trips through the kernel and backup and so forth. And in some applications, we've seen upwards of 20 or 30% performance improvements simply by avoiding all those trips through the kernel, which if you do native development, how many folks here do native development? Quarter of the room? Cool. That 30% is often very welcome. Excuse me. Now, on the managed side, we also sit on top of a concurrency runtime known as the .NET Thread Pool. Now, this isn't the .NET Thread Pool from .NET 3.0 and .NET 3.5 and so forth. This is a revised version of the .NET Thread Pool for .NET 4.0. And there's another talk, I think, tomorrow that's going to dive into the managed stack. But suffice to say, there's been a great deal of work in the thread pool in .NET 4.0. We took a lot of the lessons that we learned from our native stack and our prototypes for doing things like work stealing and kind of algorithms for better efficiency on higher core machines. And we rolled all of that into the internals of the .NET thread pool, working very closely with the CLR team. So the thread pool itself is now capable of scaling out better to multiple cores, as long as you're using the programming models that are described on this slide that sit on top of it. The thread pool itself has also gone a lot of work. It actually takes advantage of some of these data structures that I've talked about internally to just make its processing faster. So I think, I don't remember the numbers, but it's something like, just for work item throughput with the thread pool in .NET 4.0, it's about twice what it was in .NET 3.5. Just from using lock-free queues and some intelligent spin weights and spin locks and so forth. Now, the thread pool itself does have its own sort of task scheduler and resource management layer. The task scheduler is what's executing these work items. And that's sort of the corollary to the native side. And the resource manager, well, the thread pool has a fixed number of threads that run over, or rather, a set of threads that runs over all of the app domains that may exist in a given process. So even if you have 600 app domains, it's not going to create 25 threads times 600. It's going to have 25 threads for the entire process that all 600 app domains share. And the thread pool is responsible for, in effect, sharing those resources between all of those app domains. A third piece that's been really cool work that's been done in the thread pool has been around figuring out the optimal number of threads to have at any one point in time. If you're familiar with the thread pool, how the thread pool did thread injection in kind of .NET 3.5 and earlier, it had basically a daemon thread that sat in the background and would watch to see whether maybe every 0.5 seconds, if no work was happening, it would inject a new one. Now the thread pool actually uses a hill climbing heuristic that kicks in after every certain number of work item completions and tries to, see if I get this right, maximize work item throughput while minimizing number of tasks. Minimizing number of threads. So it'll continually test and see, hey, will more work items complete if I inject another thread? If yes, will more complete if I inject another thread and another thread? And if it continually is able to increase throughput, it will continue to inject more threads, obviously up to a limit. At some point, though, the curve starts, it's going up and up and up. More threads equals more throughput, but eventually more threads equals more context switches equals less throughput, and it starts going back down. And so the thread pool zeroes in with this hill climbing algorithm on that kind of upper point. And because it's continuously doing this, if the workload changes, it'll shoot back down again or shoot further up. So it very quickly adapts, which is also very useful for these parallel workloads where you're running bursts of stuff in parallel and not in parallel and not. It's able to quickly ramp up the number of threads to support that and back down. There are a few bugs in beta 1 that you'll see. If you have really long-running processes, the thread count might grow a little bit more than you want it to, but those have already been fixed for after beta 1. Then finally, and certainly not least, we've done a lot of work in Visual Studio 2010 for tooling support, both debugging and profiling. And I'll do some demos of that just in a few minutes. So actually, well, I'll do that now. All right. So let me go back to my quad-core machine here. And I'm going to open up a different project. For whatever reason, our team really likes ray tracers. It seems to be kind of the thing you do to earn your stripes is you write a ray tracer. So we've got a few different ray tracers. Oh, wrong one. This ray tracer is written in C#, and it's implemented with LINQ. And in fact, for those folks who believe that LINQ is just for simple queries, this will kind of prove you wrong. This is the largest LINQ query you will probably ever see. It's a ray tracer implemented entirely in one LINQ query. Now, I'm not recommending you write this code. In fact, I'm not even sure I understand this code. But it'll prove my point, which is that things like plink can be applied to very complicated operations like this. So I've got this query. It's a fairly pedagogical implementation, so it's a bit on the slower side. But regardless, I'm going to run it. This is the sequential version running, basically generating a color for each pixel to map out the scene. And you can see I'm using exactly, in fact, 1/4 of the CPU resources on this machine. I want to run this in parallel. And to do that, I basically copied the query and added .asParallel onto it. You can also see I've also added this with cancellation. This is new support we have in .NET 4.0, not only for plink, but across all of our programming models. Excuse me. This will teach me not to drink soda while talking. Across all of our programming models, the ability to pass around a cancellation token to all your asynchronous work. And then if you ever want to stop all your asynchronous work, you just fire that token, and everything monitors that token, wakes up and says, hey, I'm done, great. So I've taken advantage of that with this with cancellation method on plink to allow me to stop the plink query while running. So we can see that the sequential query took 9.6 seconds. I run it in parallel. You can see multiple threads getting involved in the processing here, and it completed in just under 3 seconds for a 3.3, something like that, x speed up. So instead of just running it, I'm actually going to run this under the new performance analyzer that we have built into Visual Studio 2010, assuming Visual Studio 2010 decides to respond. So if you're familiar, well, first, how many folks are familiar with the profiler in Visual Studio in previous releases? Wow, OK, just a handful of folks. So just to summarize, in previous releases, these top 2 buttons were basically here. Sampling and instrumentation. These were mechanisms whereby you could profile your code, and it would tell you which functions were your hotspots, which paths were taking the most time, which is really, really cool for optimizing sequential applications. It's not as great for optimizing parallel applications. So one of the things we've added in Visual Studio 2010 is this new concurrency profiler, which collects thread execution data and then maps it out in several different views that allow you to get a better sense for how your program is actually executing. So right now it's started up. It's launched its collector. I'm going to run the sequential version. So it'll just take about 10 seconds. I think I can. Run the parallel version. Runs much faster. Yippee. And now I close that. So while I was doing all of that, both the kernel logger and this user mode logger were logging events that were being thrown, both from the application and from the kernel in terms of things like when context switches were happening, when work was being done, when things were blocking, and what they were blocking on. So right now, it's loading up a significant amount of data that was just collected. And it's going to start processing through it. Now, this processing isn't going to be as good as it could be because I'm not connected to our corporate network right now. And because I'm using an internal build such that I don't have public symbols for this, the profiler isn't going to be able to show me as much information as it otherwise would. And you'll see at the bottom here that it's saying it's failing to load symbols. But we'll still get a great view. We would just get even cooler, or even better information if I had symbols. So it's processing through all this information, chug, 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 chug. And eventually, here we go. It comes up with some summary information, and then I can dive into the specifics for my application. So here I can see a view over the lifetime of that run, what things were doing. Green is my application was executing. This striped orange is other things on the system. So there was, this application wasn't the only thing running on the system. And gray is idle time, idle processing time. So if we zoom in on this, we can see that here I was running sequentially, and obviously there was a heck of a lot more that I could be doing because a lot of my system was being wasted. If I zoom in here, we can see that in my parallel version, I was actually doing fairly well. I was almost using 4 cores the entire time, and when I wasn't, it was because of other processes on the system. So even just this view would allow you to say, if I was kind of analyzing a sequential application, it would allow me to say, I see that there's a portion here where there's more that I could be doing, and then I can zoom in and figure out what I could be doing in that area to parallelize. If I'm using this code, or if I'm looking at this, I can say, well, I was doing pretty well, I'm done. Or I can say, if I didn't see what I wanted to see, there's more that I could be doing, and I can go in and kind of tweak my parallel application. There are some other views here that are also really interesting for zooming in. For example, there's the thread blocking view. Let me zoom out. The thread blocking view shows you over the lifetime of your application what all of your threads were doing. So these were all the threads that appeared in my application over the lifetime of it. And we can see that really all the processing, the green here, was happening on these 4 threads. So I'm just going to zoom in here. And you can see that I can zoom in pretty far. And I can see this thread deep in here happened to block. And I can see exactly what it was blocked on. In fact, I get an entire stack trace that shows me what it was blocked on. And this is where having symbols would come in really handy. I think this is actually the GC. I'm not positive because I don't have symbols. But I think this is actually the garbage collector kicking in temporarily and interrupting this thread. So let me zoom back out. You can also see things like when memory management was being done, when threads were blocked, when threads were explicitly calling sleep, when threads were doing I/O. In fact, if I zoom in up here, I can see I/O that was happening. These are disk reads and writes. So I can zoom in here, and I see I was reading windowsbase.ni.dll. So I was actually loading a native image here and this is showing up in my timeline. So if I see that I'm getting some poor performance at this particular point in time, I could attribute it to this particular read or write operation. There is a whole lot of stuff you can do with this, and I'm not going to dive into it. But we'll have lots of tutorials that'll come out around the beta 1 timeframe that will demonstrate kind of the really cool things you can do with this tool.
I have a question.
Yeah, sir.
On the last graph that was showing the percentage of the CPUs,
Yes.
and let's just say, for example, we saw a 1.2 where it drops or where it spikes. Can from this graph we also see what functions were active? Is there a link between the two things?
That I don't know. There isn't in this build. I don't know if it's planned. I think the question is, let me know if I get this right. If, let's say I was zoomed in here and I really want to know what's going on, is there a way for me to immediately get from this point to jump to the other one? I don't think there's a function that allows me to quickly do it with a command. However, if I just switch to the thread blocking view, I am aligned at that particular point in time.
Okay.
But I don't know if there's any sort of jump to that view kind of right from a context menu planned or anything like that. So the last view that's provided here is a core execution view. Let me zoom back out. This view will show me not threads, but cores, and then assign a color to each thread and allow me to see where my threads were executing on my cores. So if I wasn't using one of these managed runtimes or native runtimes, which tries to manage affinity well, I was doing threads myself, I could look at a region like this and say, holy cow, this thread was jumping all over the place. What was going on? If this was a really performance critical piece of code, maybe I need to affinitize it to one core in order to get better cache behavior or something like that. So you can get some really interesting views. If I zoom in here, in general, we can see that the runtime was doing a pretty good job of keeping threads in one place, thereby maximizing performance and so forth. All right, so some other demos. Are there any more questions on that before I move on? First the gentleman there, and then in the white shirt.
How much is that is managed versus native?
The question is, specifically with tooling?
Is it available in both managed and native?
So the question is that profiler view available for both managed and native? Absolutely. It provides the exact same behavior for both. I believe on native, we actually require a bit more in terms of symbols to be available, so you might see a little bit less if you don't have symbols. But from a functionality perspective, all of the tooling we're doing is wherever we can equivalent on both cases. I say wherever we can because some of the programming models are slightly different on the native side. And at least in the debugger view, there's a slightly different information that's provided, but it maps directly to the programming model that's provided. Let me just do one more example to highlight both some of the new programming models and the analyzer. Sorry, I forgot.
Yeah, from a debug perspective, beyond the profiling and drilling down into that, what other new facilities have you added in Visual Studio 2010?
Cool. So the question is, what new facilities for debugging have we added in Visual Studio 2010? Can I hold off on that for about 5 minutes? Great. All right. So my project here is a simple morphing application. Morphing was big when Terminator 2 came out and the Michael Jackson black and white video and all that kind of stuff. I find it really fun. So I have here 2 images, Katie and Tom. And I guess we can see what Suri looks like when she grows up. Rather than kind of taking the time to draw out the lines here, I've already drawn them out ahead of time. And I've got my kind of 1x and my 4x version. Actually, let me show this on the 24-core machine. It's a little bit... Well, no, I'll do it here. That's fine. So if I run this sequentially, output, the first image comes up fast because it's just originally, Katie's original picture. And then we sit here and kind of wait for the next frame to come along. And eventually get the next frame. And it's a little bit painful kind of waiting for this processing to happen. So I'll switch over to the parallel version. With the parallel version, we can actually see we're getting frames much faster. Frame, etc. I'm pegging the CPU, and so forth. And very quickly, we get to see a slightly horrendous image. Stop it right there. All right. So the actual code for this isn't using plink. This is using the task parallel library, if I can scroll down to the right place. And it's taking advantage of a new class in the task parallel library called Parallel, which is in the system.threading namespace. This is basically processing with 2 for loops here, looping over the height and width and computing kind of how the image is shifting onto the new image. And in the parallel version, I've replaced that outer for loop with this parallel for. So you can see if I just zoom out a little bit using the new WPF editor. Very nice. I don't know what that's good for besides presenting, but I love it for presenting. I basically just replaced that outer for loop with this parallel for, and you can see this is really a method call, and it ends with this parenthesis semicolon, such that here we basically have a delegate that we're passing into this parallel loop. You can also see we have support built into this parallel loop for things like breaking out of the loop early. So instead of the break keyword, I'm actually signaling to the loop, hey, I'm done, stop all the other iterations. And this happens when someone clicks the cancel button. So I'm going to run this one more time under the analyzer. The reason for this is I want to show the kind of interactions that these new programming models have with the analyzer. So I'm just going to start with the parallel version. Excuse me. And I'll just run this for a couple frames. Again, I will spare you the horror. So I'll run that. And one of the things we do, in addition to all events for things like when threads are executing and when they're not, we actually output special events from the parallel loops so that you can actually see where these parallel loops and p-link queries and so forth were showing up on the timeline. The reason you didn't see it for the p-link query was we don't have it yet in this build, but it will be there. But for the parallel loops, we do. So if you see areas where you expect it to be running better than you are, this will kind of point those out to you. And again, to the gentleman's question, this works for both the native models and for the managed models. Yeah, there it is. All right, so if I switch to the CPU utilization view, we can see that there were these kind of spikes. So obviously, there's more that I could be doing in this particular region here to kind of potentially get better parallelism. But if I look at the thread blocking view, we'll see these kind of blue lines that signal where certain regions. So this represented one parallel loop, and if I sort by execution, I can see that in fact, this is where a particular parallel loop was running. There's something interesting here, which is that this thread actually, even though the parallel loop didn't end till here, this one thread was running much longer than the rest of the threads were. And this is what partially accounts for those dips that I was seeing. I have a load and balance problem where one thread is actually ending up doing more work. So now that I've kind of analyzed this particular thing, I can figure out why I have this load and balance problem, which I was able to very easily see from these markers showing me where the loop actually ended, and that it didn't end until this particular thread completed. And now I can go back and do some more investigation to figure out how I can fix my problem.
I have a question about
Yeah.
that. Those are custom events you guys have in that framework, but is there an API to that we could use to send those events to market?
The question is there an API that will be used to send those events? Not in the beta, but it is planned for the release after that.
Please, that'd be great.
I think I forget what it's called. There's a name for the API, but it's going to be published. The tool is going to recognize certain ETW events with published GUIs, and then we're going to release the code kind of for a small library that will output events that match those GUIs, so you'll be able to just kind of instrument it. I think the APIs are actually going to be published as samples, but you'll be able to fully use them. All right, so now to the gentleman's question around debugging. I figure I'll use another sample to show that. This is an application for doing matrix multiplication, which is another one of our favorite examples because it's embarrassingly parallel. What this application does is it has matrix multiplication implemented in several different ways. Let me just make sure I don't have breakpoints set. Okay. So we have matrix multiplication implemented in several different ways. The first way is kind of the typical, looping over the rows, the columns, and doing the order n cubed typical algorithm you learn in college for doing matrix multiplication. The fairly naive, slow one. So that took about 12 seconds. Now we've got a parallelized version where I simply replaced the outer for loop with a parallel for. It didn't do all that great on this particular run. It was about 2.7x. Now I have a faster sequential algorithm called Strawson's matrix multiplication, which for big matrices, basically reduces the algorithmic complexity from order n cubed to like order n to the 2.8 0.83 or something. But when you're dealing with a large n, that actually makes a significant difference, as you can see here. On 1,000 by 1,000, my relatively naive implementation of Strawson's was basically twice as fast as the original version. And then I further went ahead and parallelized Strawson's for another 3-point-something x over, or 2-point-something x over my, my sequential Strawson's. Now, the interesting thing about the Strawson's algorithm is that it's based on tasks. So this highlights a new feature that we have in .NET 4.0 that lives in the system threading task namespace. And I'm not going to talk about it a lot here because I have a whole chalk talk on it on Thursday. I'm going to do a deep dive into tasks. So if you're interested, definitely come along. The basic idea here, I'm just going to zoom out to give you a sense. In the Strawson's algorithm, we generate 7 intermediary matrices. So I'm just going to highlight them here. I do some adds and some multiplies and whatnot. And I end up with these 7 intermediary matrices, all these guys. And then once I have those 7, then I generate the output array kind of by recombining those into 4 output quadrants. So to do this with tasks, I'll just zoom in on a particular one. I've simply outlined, kind of surrounded, 5 minutes left. I've simply surrounded this particular kind of subcomputation with a task. I've done that for each of these 7. And then I'm going to block waiting for all 7 of those to complete, kind of waiting on all these 4 tasks. And then I'm going to do my remaining 4 to generate the output, and again, wait on those things. So I'm going to set a breakpoint here just to show you what this looks like when I'm debugging. And I'll run this again. And again, this should probably take around 12 seconds. All right. So now I'm broken. Now, if I were doing typical debugging, I might go in here and I might go and look at my threads view. Now the threads view has actually been enhanced for this release. There's some more kind of searching you can do and interesting information and whatnot. But I'm still kind of hunting and pecking through here to kind of figure out what was going on. It doesn't represent the programming models that I'm using and so forth. So instead, what I'd really like to do is understand what everything in my system is doing at this one moment. And for that, we've added the parallel stacks view. So I can look at my parallel stacks. There it is. And let me zoom out. So now I can see, kind of from a distant view, these are all the threads in my application and all their call stacks. Now I'm going to turn off external code to make this a little bit cleaner. And I'll zoom in a little bit. So we can see that I have 8 threads in this application. All of them started in external code. This has the same meaning of external as the rest of the debugger. Excuse me. One of them is off here running program main. One of them is off here through this code stack. One's off through this code stack. And if there were multiple threads that shared the same stack, they'd all be grouped together. So now you get this very concise view, and it's fully interactive, right? I can zoom in here, and I can jump around, and I can switch to all this kind of, everything I would normally do in the debugger. But I get this nice picture, and I can pan around this thing. I can zoom around it if I were really zoomed in. Then I can pan around, and you kind of see your entire application. And with multi-monitor support in VS 2010, I actually like having this on a second monitor. And then every time I hit a breakpoint or something, I see kind of the entire state of my multi-threaded application on my second monitor. I find that particularly nice. This view also supports the task model. So while this works for an existing application, I'm using tasks, and I want to see this view in terms of tasks. Now, rather than seeing all the extra goop, I can see this just in terms of the tasks in my application. I see I have 12 tasks that started life in this anonymous method here, went up into multiply parallel. 8 of them went off this way into external code. 1 of them went off this way into multiply serial. If I show the external code, we can actually see that the external code there was actually it's calling task.waitAll. And if I look at this, I can actually see what it's waiting on. So I can actually see that it's waiting on a whole bunch of tasks and their IDs, and I can jump around between them and so forth. Now, this may be a good view for seeing what's happening in my application, but it doesn't provide me a whole lot of information on the rest of the tasks in my system, which I can get if I go look at the parallel stacks view. Now, with parallel stacks, I can see things like what are all the tasks that are waiting? And if one's waiting, what's it waiting on? So in this case, task 94 is waiting on all these tasks. And this waiting information doesn't just show you tasks waiting on tasks. This shows you things like tasks waiting on monitors. So this will actually show you what particular lock a particular task is waiting on. And if it detects that there's a deadlock, it'll actually show you that too. It'll say, this task is waiting, task 1 is waiting on task 2 is waiting on task 1, and it'll have a big red stop sign saying deadlock, if it could detect it. You can also see things that you couldn't see with the thread pool in .NET 3.5, for example, what's currently scheduled. So these aren't running. These are things that are just sitting in the various queues, and we're able to go mine those queues and show you all the tasks that will eventually execute. And you can see what they'll actually run when they get there. In this case, I'm using anonymous methods, so it's not showing me all that useful information, but I can jump around between this and the code. I can also view information. Tasks provide a parent-child view, or the notion of parent-child relationships. So I can actually go in here and say, okay, my root task is task 18. It's blocked basically on all these subtasks that are also waiting, and then these 2 scheduled ones. I can eventually go in here and see that this guy's running, and not only is he running, but he's queued up a bunch of other scheduled tasks. So there's lots of support here for kind of understanding what your application is doing, as well as how it maps back to threads as well. So you can actually see what thread a particular task is running on if you care to view it from that perspective. All right. So I am basically out of time. This guy is beeping at me. Okay. But what I will say is there are just a couple more slides here. You can review them on their own. I just wanted to kind of give some sense of things that you could do to kind of take advantage of all these cores. Things like offloading work, going faster when you can using parallelization, processing more data in the time that you have, and doing speculation. So just like I've mentioned, processors do some level of speculation. You can also do speculation where you could, say, pre-compute something, and if you don't need it, throw it away. But you were able to potentially run faster if the developer actually wanted that. Let's see. A couple things. We'll skip through these. Again, I'm happy to talk about these after my time. Things to check out. And if you have any questions, I will hang out outside the room. I'm happy to stick around for as long as people have questions. Do fill out your evals, whether you like the session or not. And thanks for coming.